9, 8,
7, 6,
A
5,
critical new
4,
warning system is taking
3,
shape
2,
deep in
1,
outer space.
0. And liftoff. The Falcon takes flight, propelling the Deep Space Climate Observatory on a million-mile journey to protect our planet Earth.
On February 11, 2015, a Falcon 9 rocket lifted off from Cape Canaveral, carrying one of the most important satellites ever to be sent in space, the Deep Space Climate Observatory, or DISCOVER. Once reaching its orbit 100 days later, nearly 1 million miles from Earth, and 93 million miles from the Sun, DISCOVER became the newest weapon in a growing battle to protect our planet against a potentially devastating threat. Massive waves of highly charged solar particles that periodically erupt from our very own Sun.
We don't understand the Sun, and when we look at it, we're trying to figure out how does it work? And a lot of that is, how does it work so we know how it affects us?
$93.5 million miles away from Earth, most of us are completely oblivious to the extraordinary activity taking place on our Sun's surface. The Sun gives us warmth and light as we go about our daily lives. It fuels weather patterns that bring nurturing rains, and ultimately gives rise to virtually all life on our planet. But our Sun also has a dark side. It can produce powerful solar flares, and even more violent coronal mass ejections that could potentially cripple most electronic devices, communication networks, even the very power grid we depend on every day.
Well, the worst case scenario would be something like another Carrington event, or perhaps even stronger, occurring now. In today's highly technologically reliant society, you'd have much, much greater effects on all of our infrastructure in a Carrington-like event.
The Carrington event was one of the strongest solar storms ever recorded. On September 1st, 1859, British astronomer Richard Carrington was observing the Sun when he noticed a bright flash. Less than a day later, telegraph lines across America and Europe began to spark and flare, completely frying large swaths of the network. Outside, an eerie glow illuminated the night sky. For the first time, millions of people outside the polar regions were treated to a brilliant display they'd never witnessed before: the aurora borealis.
Magnetic storms and auroral storms had been seen for centuries, of course, but there was no direct link between those and the Sun until the 1859 event, in which Richard Carrington saw a very large flare go off on the Sun. This was the first, at least in Western times, recorded instance of an observation of a solar flare. Within about 17 hours of him witnessing that flare, there was a gigantic magnetic storm on Earth, one of the largest we've ever recorded. This caused aurora to go all the way down to Central America and Cuba. Typically, the aurora are confined to the polar regions. You're lucky if you see them in the northern United States at times. The aurora, in this case in 1859, was very, very bright all the way down to Venezuela, Cuba. We have reports from Hawaii of the aurora in that storm.
A solar storm of that magnitude could have a devastating impact on critical communications, banking, and transportation networks. It could also damage millions of custom-built power transformers that could take months to replace.
And if you have large amounts of this charged material coming into the Earth's atmosphere, it can actually disrupt power grids. It can blow them out. So basically, it can introduce surges of power into our power grids and take down large power grids across the world.
The most recent and most impactful storm was probably in 1989, when there was a large-scale blackout of the Quebec power system caused by a coronal mass ejection. And that was a Storm not quite as large in terms of magnetic effects as the Carrington event, perhaps.
On March 13, 1989, it took only 75 seconds for an electrical current from the aurora to penetrate the ground and cause a catastrophic failure of the Quebec power system. For 7 hours, the 3 million residents of Montreal were without power in the dead of winter, shutting down almost all forms of transportation. If it happened today, a Carrington-level solar event could create unprecedented panic and chaos. Scientists believe it could cost the U.S. alone more than $3 trillion and leave millions of people along the densely populated eastern seaboard without power for up to a year. Our ability to forecast what the sun will do is surprisingly limited, considering it's our nearest star. The sun contains 99.9% of all mass in our solar system. It's so big, in fact, that you could fit 1.3 million Earths inside it.
Energy that's produced in the center of the sun takes about 30,000 years to get to the surface. So when we're looking at the surface of the sun right now, we're looking at energy that's produced 30,000 years ago.
Near the center of the sun, we know that immense pressure is forcing hydrogen atoms to combine to form helium, in a process known as nuclear fusion. The energy released is equivalent to billions of hydrogen bombs going off in the core every second. The sheer size and immense power of the sun are hard to grasp and make it extremely difficult to study.
We can see very, very shallowly into the sun. We can't see down to the center at all. So everything that we know about what goes on in the sun is either from the energy that comes out on the surface of it, and we mix that with theoretical calculations, say, okay, we know what's going on at the upper layer of the sun that we can see. Let's use theory to calculate what's going on right under that.
The sun is monitored continually by telescopes both on the ground and in orbit. And the two things you really have to monitor about the sun are the radiative output, the photons, and the magnetic field. So the photons are monitored with a traditional telescope, looking at the light output of the sun. But we also look at all the wavelengths that we can coming out of the sun. So there you need an orbiting telescope, all the way out to radio wavelengths. So we have ground-based radio telescopes looking at the sun, monitoring its radiative output continually.
Scientific study of the sun began in the 1600s, when Galileo discovered he could observe the sun's surface by projecting an image of it onto paper. He was surprised to learn that the sun wasn't perfect. Dark splotches littered its face. And when he stacked his daily sketches together into the world's first flipbook movie, he realized something else. Those splotches and the entire sun were actually rotating. Sunspots are relatively cool areas on the sun's surface, caused by intense concentrations of magnetic activity. They can grow to more than 20 times the size of Earth and provide a warning for some of the sun's deadliest eruptions.
So we have a lot of observatories around the world looking at the sunspots on the surface of the sun. And for well over 100 years, there have been sunspot counts. People have counted the number of sunspots on the sun every day to tell us how active it is. The spots are the result of magnetic fields that get twisted underneath the surface of the sun, and we can watch those spots come and go on more or less an 11-year cycle. So the sun has an 11-year cycle of twisting up its field lines, producing these spots, then they go away, and then they come back, and then they go away. And again, this is on an 11-year cycle more or less.
Anytime you see a sunspot will typically have another sunspot, its twin, which is the opposite magnetic field polarity. So they tend to come in pairs, or at least in magnetic polarity pairs, and they represent very, very intense magnetic fields, thousands of times more intense than the Earth's magnetic field. And what they do is, because of the intense magnetic fields, they suppress the normal convection or heat flow in the sun, and therefore the light, the heat, everything you see when you see the sun is sort of blocked by a sunspot, and that's why it becomes a dark, visible dark spot on the sun.
In spite of all the work that's gone into tracking and studying sunspots, we still know remarkably little about why they occur and the impact they could have on our planet.
There was a time in the 1600s where there were no sunspots recorded on the sun for decades. It's called the Maunder Minimum. And if you look at artwork from that time period, especially in Europe, you'll see that there are some rivers that are frozen that haven't frozen since. We don't know why the sun lost its activity for several decades. We don't know why it stopped producing sunspots. We don't know why it started producing sunspots again. We don't know when it can happen again. That could happen at any time. What we do know is that when the sun changes its activity, when it's no longer doing what we're used to it doing every time, it can affect us quite a bit.
Scientists aggressively monitor sunspots because they're the key to forecasting dangerous solar flares and the even more devastating coronal mass ejections they can produce that spew vast clouds of magnetic solar plasma out into the universe.
A solar flare is, again, tens of thousands of hydrogen bombs in terms of its energy intensity. It's a huge, huge event compared to anything we have on Earth. And coronal mass ejection has been likened to having hundreds of thousands of tons of material come out of the sun at 5 million miles an hour. So if you could imagine hundreds of thousands of battleships, for instance, in terms of tonnage of weight, coming out in a few seconds in one gigantic eruption. That's what we're looking at in terms of a coronal mass ejection.
Our only protection from these extraordinary events and the daily bombardment of radioactive particles from the sun is the Earth's own magnetic field.
If the Earth didn't have a magnetic field, that would be very dangerous to humans, actually all types of life, because that's radiation. And if we didn't have our magnetic field of the Earth protecting us, that radiation would get into your DNA, mess with it, mutate it potentially, destroy it, and it would make it very hard for life to live. So we rely on our magnetic field to protect us from this gentle breeze from the sun.
Hardly a gentle breeze. Our sun is sending us wave after wave of electromagnetic and radioactive material that's a constant threat to some of our most valuable assets on the planet.
This stuff is actually important to us because it interacts with the Earth. If you have enough of that material coming off the surface of the sun, it can actually impair some of the communications on the Earth. You can ionize some of the upper regions of the atmosphere. Ionize means that you can take some electrons off of the atoms, and that causes you to have a charged region in the atmosphere, and that disrupts radio communications that rely on bouncing signals off the upper atmosphere.
Possibly the most vulnerable is our global aviation infrastructure, where radio communication is critical.
Anytime an aircraft is flying, they have a requirement to report in on regular intervals using radio to the ground station so that they know the aircraft is okay. During a large solar event, those radio communications are completely unavailable. So a polar aircraft flight will not be able to communicate with its ground stations during a large solar flare, for instance. Typically, they're either rerouted or they lower them in altitude because not only do they lose communication due to the solar flare effect on the ionosphere, but there's a large outpouring of charged particles or particle radiation.
With so much at stake, scientists around the world are searching for ways to provide more advanced warning and gain a finer understanding of the greatest potential threats.
Three big outputs from a solar eruption are the electromagnetic radiation, the flare, which arrives at the speed of light, and then the coronal mass ejection going about 5 million miles an hour coming out as a magnetic cloud afterwards. But ahead of that magnetic cloud, you have a shock wave that actually accelerates particles to near the speed of light. So after the flare, the next thing you see are these electromagnetic particles coming down before the arrival of the coronal mass ejection.
The initial and greatest threat from space weather will not be directly to planet Earth, but to the over 1,000 telecommunications satellites that are in orbit and provide every imaginable convenience from GPS to phone service to military surveillance and research. Geomagnetic storms can penetrate the outer shells of satellites, disrupt communication, destroy electrical systems, and cause premature re-entry, as it did for Skylab in 1979. In the U.S., a small fleet of NOAA and NASA satellites and telescopes continually monitor the sun in a variety of wavelengths, allowing officials to issue warnings roughly 30 to 60 minutes before the most energetic storms strike. The scientists and engineers who prepared NASA's Discover satellite for its 5-year mission hope it will increase the amount of warning time up to a full 24 hours or more, and provide more precise data on where the worst effects will be felt.
Recovery has acquisition of signal.
Standing by to pass through the maximum aerodynamic
Vehicle is
pressure.
supersonic.
After launching in 2015,
Falcon 9 is supersonic.
Discover traveled more than 1 million miles to its new watch post in space, a point of equal gravitational pull between the Earth and the Sun. These are some of the first images it returned, looking back at our planet with its epic polychromatic imaging camera that's being used to study Earth's atmosphere and climate. Building on Discover's advanced suite of solar warning instruments will be an even more ambitious mission, designed to gain a deeper understanding of the Sun than ever before. This is the Parker Solar Probe, or Solar Probe Plus, a $1.5 billion experiment set to be launched in 2018. It will travel up to 430 miles a second and eventually dip into the Sun's atmosphere, the corona, to get the closest look yet at where devastating coronal mass ejections are born. It will take years for the Parker Solar Probe to make its hazardous approach into the Sun's corona in a series of enormous elliptical orbits. But scientists hope the data it gathers will ultimately allow them to better understand and forecast major solar events with far greater lead time, so that better preventative measures can be developed to protect sensitive electronics and our vulnerable power grid. Until then, the world will have to continue to rely on the somewhat limited knowledge we've been able to glean from more distant observations of our violent sun.
It is a bit surprising with our sun. It's the closest star to us by far. We have an incredible amount of data on it. We can measure its magnetic fields, we can measure the material coming off of it, we can measure the energy coming off of it extremely well. We still don't know everything about it.